Hello, good afternoon. Good morning in the US. Welcome to today's webinar about the leakage inductance model of Frenetic line. Today we have with us Richard, which I'm not going to pronounce his surname because I'm sure I'm going to commit a mistake. And Richard is a research scientist at Frenetic. He's focusing on the developing, extending, and improving magnetic models. Richard developed his passion for modeling magnetics during his PhD at the Laboratory for High-Power Electronic Systems at ETH of Zurich, where he graduated from in 2023. In his PhD, Richard investigated analytical models and optimization of magnetic devices with focus on accurate and fast transformer leakage inductance modeling. And Richard has co-authored and reviewed multiple papers for renowned power electronic journals and conference, and won the ICPEIA Student Paper Award in 2021. So Richard, we're very glad to have you here today to present the leakage inductance model. Please, the floor is yours.
Yeah, thank you, Lucas, for the kind introduction. A good evening from Zurich, and well, good morning to the US, good afternoon and good evening also to Madrid and to wherever you may be. So as Lucas already told you, I will talk about the leakage inductance model that we now have in Frenetic Online. And basically this model is a result from my PhD. And this talk is about to give you the data and show you how the model works. So that said, let's dive right into it. First, to start with a small outline, I will talk about fundamentals and backgrounds to give you some context. I will move on to how to model leakage inductance, and I will present the Quasi 3D leakage inductance model. And I will give a conclusion, and in the end, Lucas will show you an example in our Frenetic simulator. So let's start at the very beginning. Most of you probably remember, even from high school, the basic scheme of a transformer, where you have two or more coils on a magnetic core, and current through one winding excites a magnetic field, and the magnetic field is linked then to the secondary winding where an electric voltage is induced. This way you can transfer energy from one side to the other without physically interconnecting them. However, there's always some part of the field that does not couple both windings, and this is the leakage field. This leakage field is due to the imperfect magnetic coupling of the windings, and current is always required to build up this field, which leads in our equivalent circuit to a series inductance, and this series inductance is the leakage inductance. What does this have to do with power electronics? Well, in power electronics, we have several galvanically isolated converter types that are, for example, the dual active bridge, flyback converters, resonant converters, and many more. And since the leakage inductance of the transformer resembles a series inductance in the circuit, it obviously affects switching behavior, so it is crucial for the operation and the design of the converter. Which value we need for the leakage inductance depends on the converter, but what all of the converter types have in common is that we need a prediction of the leakage inductance before we can design the converter. So we need a model. But how do we model leakage inductance? So let me start from the very bird's perspective, from the very top-down approach. In the beginning, there were electric currents. And electric currents excite a magnetic field, and the relation is given by Maxwell's equation. Each magnetic field always comes with magnetic energy, and from the magnetic energy, one can then derive the inductance. There's also other ways on how to calculate leakage inductance, but this is a very convenient one. So if you want, you could use the metaphor of seeing Maxwell's equation as the puzzle. The pieces of these puzzle would be the mathematical solutions. Then finding or crafting those pieces would be the modeling process, which we do at Frenetic at the research and development section. And in the end, when we puzzle those pieces together, we get the completed puzzle, which in our case resembles the physical model. Okay, to get a little bit more specific, and one perspective further to the downside level, what does this mean now? Okay, so in my PhD, I mostly use the Quasi 3D modeling concept. This basically means that you split up the 3D transformer geometry into winding sections, which are shown here with the diagonally hatched background and also the rectangular background. And throughout those winding sections, you have constant cross sections. And there are two basic cross sections that we can derive from such standard transformers, which is the inside window and the outside window geometry. The name obviously coming from the transformer core window. And in the end, we calculate leakage inductance contributions of all winding sections and sum them up. For straight winding sections, the game is fairly simple. We simply calculate the leakage inductance per unit length and multiply it with the section length. For curved winding sections, it is a little bit more tricky because the windings are curved, so the currents are curved, so the magnetic field is curved. So we need some sort of radial energy weighting to take that into account. And we do this by taking the leakage inductance per unit angle and multiply it with the section angle. But how do we calculate these winding section contributions? Well, I mentioned earlier already that leakage inductance is proportional to magnetic energy, provided that the magnetomotive forces of the windings are balanced. And for getting the leakage inductance per unit length, we basically just integrate the magnetic energy density of our given cross-section over the computational domain, and we're more or less fine with that. For the leakage inductance per unit angle, the game becomes a little bit more tricky because here we have a rotationally symmetric arrangement. So we have a radial energy weighting in the integrand. Assumptions that help to solve these integrals analytically is to assume equivalent winding blocks, which we can see here, and assume frequency-independent homogeneous current density. That is typically a good assumption because in leakage inductance, most of the magnetic energy is stored in between the windings. And we have skin and proximity effects, so we have current redistributions over frequency, but this only redistributes the current in the wires, and the overall current stays the same. And since Ampere's law still needs to hold, the magnetic energy in between the windings is almost untouched by this change. But I will get to that later into more specific details. Now, let me start with the Quasi 3D model that we now launched to our Frenetic simulator. As the name already says, it uses a Quasi 3D modeling concept, which I explained earlier. For straight winding sections, we then use the model of Edouard Roux, which was published already some while ago, almost 100 years ago. For curved winding sections, we use a model that I derived in my PhD. And today in 2024, we extended this to interleaved and parallel windings because they are very relevant for industry. They are very needed. And this is why we took this adaptation. And in the end, if we puzzle those pieces together, we get the Quasi 3D leakage inductance model. Let me get to the detail about the models. So specifically for straight winding sections, we use the model of Edouard Roux. Edouard Roux was a French guy from Mulhouse, which is actually not so far away from Zurich. And funnily enough, he also studies at ETH. So he was there some while before me. Okay, but how does he actually derive the magnetic energy per unit length, and from that the leakage inductance per unit length? So he starts with assuming rectangular currents and uses the method of magnetic images to get the correct boundary values for the magnetic field. And when you assume infinite core permeability, it leads to the fact that you get the same magnitude of mirror image currents as the original currents. And when you actually check the signal, the current density distribution in space, you find that it is actually a two-dimensional rectangular signal in space. And much like a time domain signal, where you have a signal in time domain, which is rectangular, you can approximate that signal with a Fourier series. You can do this also in 2 dimensions. And the current density then is coupled to the magnetic potential via Poisson's equation. And since the right-hand side here has the shape of a double Fourier series, we also find a magnetic potential that satisfies this equation. And it also has the shape of a double Fourier series. This solution then implicitly satisfies the boundary conditions, as I already said. Specifically, this is that the magnetic field has no tangential component at the boundary, meaning that it can only be completely orthogonal. The magnetic energy per unit length, then, we can derive from those two fields, and we get a well-converging double series for the magnetic energy. The good thing about the model is that the winding positions and the dimensions can be completely arbitrary, and it is also accurate and computationally efficient. For curved winding sections, we use the rho-theta model. This is a working title. It is basically a mixture between rotated and rho, because we calculate the rotated magnetic energy, sorry, and we derive this from the potential vector of Edouard rho, hence the name rho-theta. This then results in a well-converging triple series, which we verified with 2D FEM, and we also published it in IEEE Transactions on Power Electronics. And just to give you an example of one transformer to show you how it looks, basically here you can see the leakage inductance per unit angle over the number of spatial harmonics. The number of spatial harmonics is the amount of sum terms that you have in the double series. Now, and you can see for the inside window cross-section where you have the solid line, the solution converges quite rapidly. For the outside window, you need a few more terms, because what we basically do is to use an equivalent winding window and put this far away from the windings, such that we basically emulate an outside window cross-section with the solution of the inside window cross-section. And of course, the goal now is to choose as little terms as possible, because we want to calculate it fast, and as many terms as necessary, because we want to be accurate. And 30 and 120 for inside window and outside window are quite solid choices for that. Okay, now the adaptation to interleaved and parallel windings. The good thing is about Rho's model and the potential vector of Rho is that you can basically, you calculate the Fourier coefficients of each winding separately, and in the end, you just sum all of that up. It's possible to sum that up because the magnetic field is linear. And we do the very same with interleaved and parallel windings. We basically just have then more blocks, and we calculate the Fourier coefficients of all those blocks, and in the end, we sum them up. For interleaved windings, it's fairly simple because interleaved windings are serially interconnected, meaning that we already know the current through the windings. So it's the same. So we already know the MMF. For parallel windings, we assume the current to divide equally. Okay, all core types that we have in Frenetic Online are supported, except toroids, that is, because it requires a different modeling concept. And what does the core do in the model? How is it taken into account? Well, it's actually rather simple. The core simply defines the winding sections. So you still calculate your leakage inductance per unit length or angle for inside and outside window, and then you just scale it with different lengths or angles depending on the core. For an ER core, we have an example here where we basically have the inside window angle alpha, or in this times it would be 2 times alpha, and then the outside window angle would be the rest of that. Another example is given here for an E core, where we also have straight winding sections, outside window and inside window, that is. Okay, now, like every model, this model also has some limitations. First of all, it is frequency independent. Now, a very frequent question that I get here is, yes, but in power electronics, we operate at high switching frequencies, so the model needs to be frequency dependent. Well, yes and no. Of course, we have frequency effects, but we should tackle this from the design perspective and not from the modeling perspective. And the answer here is quite simple. We just need to choose a small enough strand diameter. As a rule of thumb, if you choose strand radius over skin depth below 1/6, you are very safe. You are even quite safe, even above that. To show that, I built 3 transformers in my PhD, and basically they all have the same geometry, just they use different wires. In particular, the wires differ in the strand diameter, and the strands are insulated. Some of them are insulated and some of them are not. The copper area is as close as possible, but of course you will never find 2 different wires that are actually the same, which is why we also get a small difference in those leakage inductances. Now, and what we see here over frequency is that at a point where our strand radius over skin depth equals 1/2, so already far above that, we see that the leakage inductance is almost the same. It just drops below than 0.1%, whereas the AC resistance already changed in the case of the blue transformer already by almost 50%. And you don't want that. So if you design your transformer that the winding losses are okay, your leakage inductance will also be okay. This also has physical reasons because we have current redistributions over frequency, but these happen inside the wire, and the losses, so the AC resistance is only derived from effects that happen inside the winding, which are the losses, and the leakage inductance is derived from magnetic energy. And as we already know from earlier, the magnetic energy is mostly stored outside of the wires, and this is why a resistance is more sensitive to frequency than leakage inductance. Now, another limitation is that parallel windings assume equally distributed currents. We know that this might not be true depending on the winding configuration and the operating frequency, because there can be circulating currents in parallel wires. But again, this is an issue that we really should tackle from the design perspective. In particular, the winding interconnection should not allow circulating currents. Another limitation, which is really a limitation of the model, is that the wires are not modeled individually, but they are modeled as unified blocks. However, the error introduced by this is quite low. I've written a chapter about this in my thesis also. And the good thing is that it drastically decreases computational effort when you, for example, you only have to model 1 block and not 20 single turns. Okay, let me come to the verification. So basically, the leakage inductance per unit length and angle and the whole model was already verified in my PhD. And we published the results in papers, and you can read it in my thesis. But also to show that it also works for the interleaved and parallel windings, we also designed some transformers to show that it works. In particular, I designed 5 benchmark transformers, which we can see here. And it was it was very important that we here use diverse geometries and winding configurations. So for example, the first one is a two-chamber design where we have disc windings actually that do not fill up the window. So 1D models like Dowell's model will fail spectacularly. You cannot even apply it. The same for the second transformer, where we have windings that are only really a fraction of the window. Then we also have a transformer with parallel windings. We have a transformer with interleaved windings, and we have a combination of those two. We built those transformers with care in our lab in Madrid. Most of them were built by our really talented manufacturing engineers and not by me. Okay, why do I emphasize that they were built with care? Because geometrical uncertainties always are a pain in the ass if you want to verify models. And you want to build transformers that have a geometry that is as close to the one you model as possible. Because you want to verify the model and you don't want to investigate geometrical uncertainties, which is also an important topic, but not the topic for today. I measured those short circuit inductance with an Omicron Bode 100. It is a vector network analyzer that is based on using the S parameters, and it calculates an equivalent impedance from that. And from this equivalent impedance, you can extract a series inductance. And the inductance that we used for verification, obviously, is the one below a frequency where frequency effects are not happening yet, because again, this is also the region where you want to operate your transformer at. So, for example, here you can see this is a very fine Litz wire, and you see frequency effects are basically almost not even happening until this frequency, whereas where you have a bigger strand diameter, we see here at the end a small drop in leakage inductance, and this is actually due to frequency redistributions. Also, anyone who already measured short circuit inductances will know that at the very low frequency regime, you see a very, very, very high inductance, but this is not the leakage inductance. This is the magnetizing inductance masking the leakage inductance here. The results are given in this table. So basically for all 5 transformers, we calculated the model error, and the error is below 10% in all of the cases. And we are quite happy with that, because in the end, we will never get to 0% error because of geometrical uncertainties, because of measurement uncertainties, and also because in the end, we're modeling a 3D geometry with 2D assumptions, and we have some transition regions that we will never capture. And all of these influences combine when you compare the model result with the measurement. But we are below 10%, which we're quite happy with, so we verified our model. To come to a conclusion, we introduced the Quasi 3D leakage inductance model and verified it. We launched it to our Frenetic simulator, and in the end, this will allow better predictions of the leakage inductance, more accurate predictions, and will lead to better magnetic designs. There are always uncertainties, hence there will always be differences between the model and the reality, which we also saw in the table where we didn't have 0% error, but always some small percentage. And a more meta conclusion would be that if the physics are known, which is the case in leakage inductance, and analytical solutions are available, which is also the case in leakage inductance, these analytical solutions are actually quite viable. Why is that? Because they scale well to any geometry, because they really satisfy our Maxwell equations, and as long as we don't have material dependencies that we cannot yet accurately describe physically, it makes a lot of sense to use those analytical models. Okay, I'm at the end of my part, and now I would like to hand over to my colleague Lucas Nikieta, who will give you an example in our Frenetic simulator. Thank you.
Thanks, Richard. I will share my screen. So, you see my screen, right, Richard? Okay, so I want to just show you a couple of examples on this, let's say, where this leakage inductance model that Richard has just commented is appearing in our Frenetic simulator. This is an example of a 3 kilowatt LLC transformer where we can do having an accurate model is to really do much better designs much faster. This is an example here. If we have, for instance, a no interlift transformer, we have a leakage of 7.88 microhenries, while when we go for a interlift winding, this will reduce considerably, in this case down to 2.72, so almost 4 times. And if, for instance, now we go to a split chamber, as Richard was showing in the validation, this will lead up to much higher leakage inductance, in this case, 36 microhenries. Now, the good thing about having the right model in a simulator is that you can not only analyze, let's say, the behavior, but also optimize things, right? So if, for instance, we come here to the specification and we define that we want to have a specific leakage inductance and we want it to be integrated, one of the things that we can do is that we can try to get an optimized design, which is going to look for a core and a combination of turns and winding configuration that is going to meet or match those requirements. Like in this case, what you can see is that we get an automatic design, which is meeting or is giving us a very close value to the target series inductance. And this is one example, but another example that I want to bring to the table, which is in those applications where we have many windings, many times it's very difficult to understand what is, let's say, the leakage inductance. And this is an example of a multiple winding flyback of flow power, 11 watts, but where we have several windings. And what we can see here is that we have the primary side in the inner layers, and then we have grouped windings. So we have one winding in the third layer, then the other one, let's say the orange one underneath. And like this, we have another 4 windings. And what we can see is that the closer the winding to the primary side, the smaller is going to be the leakage. So for instance, if I take the secondary, this one, the secondary, let's say in orange, this has 3.3 micro, while if I take its counterpart, which is going to be the next one, is going to be 4.8. And if I go to the next one, it's going to be 6.4. So the farther, the larger the leakage. And being able to model or simulate so many windings and having an accurate estimation of the leakage inductance is critical, and it's very important, and especially in these applications where you can have cross-coupling between windings, which could affect the control of the converter, is really, really important. Yeah, and this is a little bit an example in our simulator. Now it's time for questions, so please don't be shy. We will be happy to answer any questions that you might have. We already have one question in the chat. We have Gen Puente who asked, how can we access the copy of the thesis from the web if the copy is out there?
Yeah, of course. It's out there. You can find it at the you can find it at the ETH research collection. So you go to something like researchcollection.ethz.ch, but you can just Google research collection ETH Zurich, and then you just type in my name and maybe the title of the thesis, and you will directly find it. So it's open source, as there are also all of my papers open source. Yeah.
I wanted to ask you one thing, Richard, which is, what is your experience and what is your experience at the time of measuring? What is the best approach for measuring the leakage inductance? Also, if you can comment on the, let's say, additional loops creation that you can have on the twisting. I mean, these kind of things that we discussed when we were doing the validation, if you can comment a little bit on that.
Yeah, of course. Well, basically, how you can never ever measure leakage inductance directly. maybe I explain this with the equivalent circuit. Let's see where we have it. Slide. What was that? Yeah, here. So basically, how you measure leakage inductance is always you measure from one side, so you excite the winding with a current, and you short circuit the other one. And what you basically do is then you bridge the magnetizing inductance, and in theory, you would only see the leakage inductance. But this is theory. In reality, this short circuit will always have a finite impedance, which is why in the low frequency regime you mainly see a very high inductance, but this is the magnetizing inductance. So this is in general how it works. And if you want to measure other, for example, if you have a multi-winding transformer, leakage inductance is always a property of two windings. So therefore, if you want to measure, you have basically in a three-winding inductor, you would have three different leakage inductances, 1 to 2, 1 to 3, and 2 to 3. And you can measure those separately. And you always measure from one side and short circuit one other. So this is the general concept. And other things that you have in reality is that from the short circuit, you also sometimes create loops. And this loop can add up to, well, this loop adds up to the inductance measurement, but it's actually not part of the leakage inductance. So what you can do to minimize this is to twist the wires and make the loop as small as possible. This is especially problematic when you have a transformer like this, the fifth one, where we have a high transfer ratio. Because when we measure from one side with the higher number of turns and we have a loop at the other side, the inductance of that loop refracts to the primary side with the turns ratio squared. And in case of this fifth transformer, actually, that was quite significant. This transformer has a leakage inductance around 0.8 microhenry, if I remember correctly, and the reflected loop actually adds some 0.5, 0.6 microhenry. So it almost doubles the leakage inductance. And if you have other transformers with even higher turn ratios, this is even more critical. And yeah, other difficulties are if you want to measure leakage inductances with transformers with high transfer ratios, is in general that you have, if you measure from the side with a high number of turns, you have the problem of the reflected secondary impedance. And if you measure from the side with the lower number of turns, you have the problem that you want to measure very small inductances, which is again some tricky. So sometimes you have to choose between those two and see what yields the better trade-off. Yeah.
Thank you. Well, we have a question also, which is, what is the most accurate method to calculate the leakage inductance for a transformer? I guess that the quasi 3D model should be the answer, right?
Yeah. That would be the most popular answer. But of course, I mean, the most accurate model. I mean, this is kind of a philosophical question, because if you compare the model with measurements, as I said, you will always have geometrical uncertainties, you will have measurement uncertainties, you will have things that you cannot control. So even with a hypothetical perfect model, you would not get to 0% error. So there's kind of, it's kind of, as long as the model is verified, it's kind of hard to actually say which one is better. But I can assure you that that the model we now have in Frenetic Online works quite well. It scales well to any geometry, and it's also fast.
Good. And what is your, I think also it's been always a topic that the people like to look at the leakage as a percentage of the magnetizing inductance. Now, my experience is that you can gap the core and then still get almost the same leakage inductance. So at the end, this percentage figure for me. It's not that much a figure of merit. Can you comment on that, on what is the impact of the gap on the leakage inductance?
Yeah, very good question. Actually, if you have, for example, an E-core transformer and you have the windings only on the central leg, and then you add a gap, what basically happens is that the leakage field, which mostly goes through the windings, through the air, it just closes through the outer leg. So in the end, the influence on the leakage inductance is almost zero. The game changes a little bit when you have gaps on all core legs, where basically the leakage flux only has an opportunity to also pass the air gap. And then you add a small share of air to the reluctance path, and then actually your leakage inductance changes. So you would get a little bit of a smaller leakage inductance. And obviously the magnetizing inductance is always affected by the air gap. Yeah, because it reduces the overall reluctance. Sorry, it increases the overall reluctance.
Okay. We have some more questions. We have Anus Suman asking what is the typical computation time of the Quasi 3D model? Well, I think you saw in the platform. I mean, the computation of the leakage is milliseconds. I mean, it's just right.
Yeah.
So fast.
Yeah, so I actually didn't even check the computation time just of the model, because in the end the platform calculates everything, and there's also the geometry happening. So I didn't check how long it takes exactly, but it's in the milliseconds or below milliseconds range. Yeah. But it anyways depends always on where you run it, whether you run it on a small laptop, whether you run it on a server. In my PhD, I mostly used calculation times to just have some sort of benchmark, but then that benchmark is always to be taken with a grain of salt. When I extracted the calculation times in my PhD, it would happen that you measure the calculation time and then you run it again, and it changed by a factor of 2 just because maybe there was some background process in the computer also happening. Maybe there was a small fluctuation in ambient temperature, and the cooling power of the CPU is a little bit less. So in the end, it's very fast. It happens in the blink of an eye. And yeah, so I can say so much about that.
Okay. And we have a very good question, which is, what about the leakage inductance of U or UR cores, especially when the primary and secondary windings are located on different ferrite poles?
Yeah, then you need a different modeling approach. So this modeling approach of the Quasi 3D leakage inductance model is based on when you have all the windings on one leg.
Okay.
Yeah. Because you will need to choose different cross sections, those will look differently. Then you will need to check how much energy do the windings contribute outside of the region that is not in between the windings. Yeah.
Okay, we have another question, which is, what is the best approach for calculating the proximity losses in resonant inductor for multi-strand lead wire construction? To answer this one, I have to say that we have another webinar that we recorded, and it's uploaded to our YouTube channel. It's about the winding losses, and we explain all the, let's say, proximity loss calculation there. So you can check it there. Then we have another question here, which says, for turn ratio measurement, usually I used to put a sinusoidal waveform with a certain frequency in the primary side of the transformer. Then I measure and compare the secondary voltage peak to peak of the primary voltage. Is this how you measure in Frenetic? The answer to this one is that we measure the impedance at the primary side, we measure the impedance on the secondary side, and then from there we can get the turn ratio. This is how we normally do it.
Yeah.
Then we have another question, which is, in a future webinar, could you go over inter and intra winding capacitance? Richard is throwing the ball.
Yes, this is definitely on the roadmap and it's in the pipeline. Yeah, this will come.
Let me see if there are any other question. Guys, don't be shy. You can ask whatever you want. There are no new questions, so I guess we will be able to. Oh, we have new one.
There's some in high frequency transformer. How can we decrease the leakage inductance? Well, you can decrease the leakage inductance by putting the windings as close as possible, because then you minimize the space where the magnetic energy is stored. And also you can choose less turns because the leakage inductance is proportional to the number of turns squared from the side you measure it.
And there is another question. Have you tried adding a negative dynamic resistance in series of the source circuit for the measurement in the secondary to reduce the effect of the series resistance during the measurement of the parasitic inductance?
How would you add a negative resistor in reality?
To be honest, I don't know. I'm trying to figure it out. And
well, I mean, with a negative resistor, this would be a paradox, because then you would create energy out of nowhere. So I think that you could do in simulations. Mathematically, it's possible, but in reality, I think that's going to be really hard.
Okay. Yeah, I think that those are all the questions. So I guess we can leave it here for today. If you there's one more question.
The questions coming in from two different channels, right?
Yeah. That could be a reference to the negative. There is one question that says, do you have any comparisons of leakage between center leg air gap transformer and three leg air gap transformer?
No, we don't. But I mean, just look at if you have air gaps on all transformer legs. Just look at the path that the field needs to cross in relation to the window heights, and you will find that, for example, if you have a window which has 50 millimeters height, the leakage path has to cross that, and then it also has to cross the air gaps, which might be in the region of 0.5 or 1 millimeter. So really, it doesn't change a lot the reluctance path that the leakage field faces. So the impact really is negligible.
Okay. Good. Then, if you guys have any other question, you can reach us. You can reach us, and we will be happy to answer any other questions that maybe today you were not able to ask. Here are our emails. And thanks to all for being with us here today. I hope you have a good rest of the day, and see you soon.
Thank you very much. Thank you for attending, and bye-bye.
Bye, Richard.
Bye-bye, Lucas. Bye-bye, everyone.